In the last of the videos of our power meter series, we looked at the design of a power meter calibrator, and in this video we're actually going to do the build on that, all the mechanical work and the soldering, etc, etc, get it tested and working. Overall I'm happy with the manufacturing of it, so I'm just going to have a quick visual inspection, and I've taken a still of this so that I'm not waving it around in front of the camera. So first impressions are these holes are somewhat large. I would normally use an M3, and looking at holes as well, I notice I've got a track very close to this this hole on this side, so that's not too clever. Shouldn't really have done that. There's plenty of room to move this track around it, so you know we can route it just over here. Really would be absolutely fine. That okay. Let's take those lines off. Power supply side then, it's not a problem, but I think on a future revision I will increase the size of these pads slightly and perhaps increase the hole size slightly, just so I've got a bit more choice on connectors. The other thing is there should actually be a slot cut through the middle here like that, and that is on my drawing. I've had a quick look to see why it hasn't come out, and the answer is that I put it on the assembly layer and the manufacturer wants it on the mechanical, so my bad. Okay, moving on. Switch section, I've got no problems with that at all. I don't think any problems there. The switch holes are the right size, the switches fit in them, the BNC holes are the right size, the BNC connectors that I bought do fit. There's not a lot else to say about that. This slot I think could have perhaps been just a little bit more generous that I've put in the board here, just to give me a bit more space, because there's a 12-way connector will be fitted in that space on the front panel. Looking at this, the chopper board, which has got the rotary switch on it, so there is a problem here. This is a section for screening, and it's covered in solder mask. It is, I kind of can scrape that off if I want to use it, but I'll have to go back to the PCB design and pull back the solder mask. Some of these capacitors, so this one here, capacitor 10, just here, it's fine. It's polarized capacitor and it's got a plus on it. So a C1 inside the chopper section, that's fine as well. But actually some of these other capacitors are polarized, so that's really annoying. So I picked the capacitors at the Altium Volt, downloaded the actual trace for the capacitor, and it hasn't got the polarity marked on it. So I'm really annoyed with that, because that'll make assembly a bit of a pain. I'll have to double check everything. My bad. I didn't mark the polarities on these plugs, P7, P8. So I know that the square pin is plus, absolutely fine. I made sure of that, but unfortunately, of course, once I've got a connector soldered to this, I won't be able to see the square pin. Yeah, so that's it really. Critique of the board done, I think. Okay, so I've chopped up the board now, and the important thing to know here is that the lines mark the bottom of each board. So we cut on the other side of the line to make sure the bottom of each board is an accurate reference. Beyond that, just used a hacksaw, nothing special. Cleaned up the edges. Okay, so I'm going to use a stencil for the soldering, and then pop this in the reflow oven. So we're going to paste it, put all the components on, except for the through-hole components, and I'm not going to put the power block on either, because although it does have a reflow profile, my reflow oven is not that accurate. I'm a little bit worried about that particular component. So just mixing up the paste. I'll show you the carton in a few minutes, and I'm using a plastic rib. So this is a pottery tool, and it's sort of medium soft, but it's pretty good for this. It's kind of, it's just squeegeeing the paste in place. Okay, so the paste is applied and now the excess removed, and this is the paste that I'm using, which can be stored for quite a long time without putting it in the fridge, and it doesn't degrade horribly or anything like that. So I don't have a huge amount of it, but you don't need a huge amount of it. Okay, quickly picking up the stencil, not smudging the solder paste, and there it is. That looks okay. I have accidentally included solder paste on the transformer, but you know, not a big deal. It'll just tin the pads when I reflow this. So now just need to go and place all the components. Just wearing a pair of magnifying goggles, placing the first inductor gently into place, and when the solder melts this will actually straighten up and pull it central. And now onto the first resistor. I'm not going to make you sit here and watch me fit every single one of them, just changing to a different pair of tweezers because that's a bit awkward. But yeah, we just need to drop each one in place and I'll come back when it's all done. Okay, so that all went together pretty well. Perhaps I should have used a microscope instead of goggles, but only a couple of concerns are the inductor L1, it's a little bit small on the board, and the two capacitors next to it, C12 and C14. The markings, which are normally on the positive end, look like they've got a negative symbol in, so I had to just double check that on the data sheet. But other than that, it's all gone together very well indeed and needs to go in the oven. Okay, so we're out in the kiln room, which has forced air ventilation, so it's quite useful to put the reflow oven in here. This is a T962A, a cheap Chinese reflow oven. It actually doesn't have the original software in or the original controller. I replaced those with my own stuff at some point in the past, which meant it could have some additional thermocouples and profiles for the fans and that sort of stuff. The other thing that I did was the tray has quite a lot of venting on the bottom and it's a little bit too much, I found, so I've put some heat resistant tape in there just to control the airflow a bit better. Okay, so board in, and we'll start the relevant reflow program. Takes 4 or 5 minutes, that's all. Okay, we're down below about 50 degrees, so we can take a quick look. And first impressions, that has soldered absolutely fine. All the solder looks good. It's a bit hard to see, of course, on the video. I'm just going to pop it in until it's fully cooled down. The fan is still running quite fast. So it's out of the oven, it's looking good. Lots of soldering to do now, just some surface mount and a few through holes to add to this one. Then I need to do the switchboard, and then I need, of course, to do the other surface mount board, which I'm going to do in the same way using a stencil. So I'm just soldering the transformer at the moment, and what I do is I apply some solder to one pin, then use that to position the transformer, and then go around and solder all the rest of the pins. So I'm going to fast forward through this now and come back when lots of soldering is complete. First board down, so I think the only thing left to say about this, I mean it's assembled perfectly well, is that the fuse and the mains connectors on the left hand side where there is potential shock will have a plastic cover. Okay, so the board had a few components missing when I came to assemble it.
Got back on track again, I think, and I delivered the missing parts in
and one that I ordered wrong. So I've ordered them, they've come, but of course this now means I'm going to have to hand solder them to the board. So as a quick demo for those who haven't soldered SMDs before, I've removed the solder from one pad and I've got solder on the other pad, because if you don't do that then the SMD device won't sit flat. I've picked the SMD device up off a hard surface so that the points of the tweezer are not below the bottom of the device. Now I slide my soldering iron onto the pad with the solder, melt the solder, put the iron in the right place and slide the device up to the tip of the iron and then remove everything. And one side is now completely soldered and the other side is hopefully lined up so that I can just use a traditional technique and add some solder into the joint. So I spin the board around so I've got better access. It's going to be slightly difficult to solder this without getting in the way, but this is a normal soldering job. So tip goes onto the pad and the end of the resistor, and then we feed the solder into the gap between the pad and the resistor, not onto the tip of the iron. That's done, so I'll just go back to the other side now and just touch up that joint there to make sure I've got enough solder in it. And that's it. Very neat SMD soldering by hand. Okay, PCBs assembled and fitted into their bracket, ready to go into the case. So this is a 3D printed bracket, and it spaces the boards 12mm apart, which is the depth of the connector between the two. So it's going to just sit inside the case, fastened to that bottom chassis, and with its knobs and connectors through holes in the front. So that's pretty neat. This printed part wasn't too bad. There are slots on the bottom for the boards to sit into. There are slots on the top, and that's all spaced out around that connector, 12mm. There are some screw holes in. I haven't put the screws in just yet. So what I'm doing here is I'm just measuring from the actual manufactured panel to make sure that all of my hole centers are at known heights and positions, because although I've drawn this for printing and cutting the front panel, things might not actually be quite where I intended. So just double checking everything really here and doing a sketch, and then I'll go back and mark everything out again before I cut the front panel. Okay, a couple of quick pointers on preparing the case. We're going to drill all of this out now, so in the workshop, but we're going to use this, which is 100% scale drawing, and it's been adjusted to take account of the measurements that I actually took earlier, which were slightly different than the original plan. So a tip for aligning this correctly is to put a fold along one of the edges so that you can actually match that up very accurately, and then you can use a straight edge or something like that to reference one of the sides. Then simply just stick it on with some masking tape. So this one's actually from it's a freebie from JLC PCB. So but yeah, you don't need to use a lot, you just need to hold this all in place. Some people use a spray adhesive and stick the whole thing down, but it's a bit overkill. Okay, first things first, we're in the garage now, and we're going to do the drilling of this panel, and we also have to cut a shaped hole in the back for the power connector. So I've stuck my template on. I've got a hole punch, and I'm just literally going to punch the centre each of the holes. I have put a little wooden block underneath here because this does have lips on it, and you need it to be supported behind as you hole punch, and also really as you drill. So I'm being as careful as I can to get that in the right position. So I'm going to use a 19mm punch for the power switch hole because it'll leave a nice clean finish and be relatively stress-free. So I'm just going to widen out the hole to 10mm, and I'm going to use a cone cutting tool for that, and that's a good thing to have in your toolbox if you haven't got one. So the punch is in two parts. You feed in the sort of support side from one side and screw on the cutting blades onto the other, and we just need a spanner to hold that in place as we get the cut started, and an Allen key for the other side, which is going to do the turning and pull everything through. It takes a bit less effort than it looks like. Okay, and there we have it. It pops through and leaves a very, very clean hole indeed. We can just tidy that up a little bit with a file to remove any burrs. So I know some people are a bit intimidated by the metalwork. My advice is get one of these cone bits or a small set. You can get them for about £10 for a set of 3. Drill your small holes as best you can. Always support it from underneath, always punch it beforehand, always make a 100% template, and you should be pretty much there with all of the round holes. So I'm just enlarging out the holes now for the BNC connectors, and they're 1/2 inch holes. So it's that good, and you can see it. These are very clean hole. There's a little bit of swarf on the inside just to be removed, but burrs I should say rather than swarf. But you can see how straightforward it is to drill a very neat round hole using one of these tapered cutters. So some drill bits, tapered cutters, and some files, and you've pretty much got what you need. Okay, turning our attention to the difficult hole on the back. So you can see I've sketched out the hole that I need to cut, and people use all sorts of methods. You can drill lots and lots of very small holes around the edge and then try and file it out. You can actually even chisel it out with the right type of tool. I'm going to drill 2 holes, which will take out the bulk of the material, and then I'm just going to use a coping saw to remove the rest. And it may seem like that's a wood tool, but actually watchmakers and people like that use those saws all the time for cutting brass and similar stuff. And just make sure you get a fine tooth saw blade for it. That's the only thing. Finally, once you've roughed out the hole, you can actually then just use a file to tidy up the edges. And just make sure you hold it very sturdily, and take your time with the filing. Just watch what you're doing, really. A good file will take off material very, very easily, particularly in aluminium. So we're back in the electronics lab. All the drilling is complete, and I'm just really assembling everything lightly for the moment, making sure everything's in the right place. So for example, the connector going in, and then I'll put the wires onto the back of that later, once I'm sure everything is aligned perfectly. So really it's just a case of assembling it all now, making final adjustments, and we will be job done. Construction is complete, so now it's time to check a few things out before trying to actually use this. It's bound to be faulty in some way or another. First up though, I'm going to trim up the voltage output to 12.8, close as I can. And then I'm going to move on and start checking the voltage divider on the switch. First of all, looking at the resistance, and then looking at the voltages that it's producing. Conveniently, the resistance can be checked using the reference out connector. Turn the power off, and basically you can measure the resistance directly. And HP provide all the details of the resistances and the voltages in the service manuals. So I fixed a missing resistor, and now I'm looking at the voltages, and I am not getting them anywhere near the range that they should be. I should be getting 1.4 volts here, and I'm just not getting close to that. So I need to do a bit of investigation. So it turns out that the power supply should have been in 15.8 volts, not at 12.8 volts. So I can actually feed that in from an external supply without any problem, because this is all modular. So just unplug the internal supply, connect up an external supply, dial in 15.8 volts, and see what we get. And what we get on the 1 milliwatt setting is 0.14447 volts, so 144.7 millivolts. And if I check that against the intended value, it should be 0.145, so it's pretty much on the money. So that's pretty good news. So it looks like that could well be the root of that problem. So just checking a few more voltages now, and really good news. They all appear to be well within the 2% tolerance that we'd expect on the voltages on the divider. Okay, although the voltages worked out okay, when I plugged it into a power meter, it was about 6.8 dB down across the board. which didn't make a lot of sense. Now, rather than show me running around looking at all the possible places, testing connectors and things like that, I thought it might be a good idea to open this up in the simulator and show you what actually went wrong. And I can talk through the process that I used to find it. So why could it be down is the question. So here is the circuit diagram that we saw in the last video, and I've just rearranged it slightly into the simulator, and the simulator I'm using is MicroCap version 12.2.05, which has got a nice friendly interface. So these are the parts that are in use, so actual transistors, etc, etc. So I've tried to do that so that should it be a problem with the transistor matching or something like that, that I can actually simulate replacement of the transistor. And there are two parts to this circuit. So on the screen at the moment, I've got a 145 millivolt battery on the input, which is representing the output from the voltage divider switch. We know that's working. We know at 1 milliwatt it produces 145 millivolts. So that's great. And then it goes into the 196k resistor that's at the start of the circuit. Then we get all of the calibrator circuit here, and then in the dotted line to the right hand side is actually the start of the circuit that's in the power meter itself. So this is the amplifier circuit, and we've got the transistor Q1 over on this side, which is across the input here. Now there's some biasing going on, which is providing voltage for the transistor to work, and there's also some DC applied to the output of the op amp. There's some filters on the feedback circuits. There are some shaping for non-linearity over here, but we don't need to get caught up too much. What is useful is that in the service manual for the power meter, it tells us that at test point 1, just over here, that we should have about minus 900 millivolts, which we do, and we should have about a 100 millivolt peak to peak at 0 dpm, which is 0 dpm, which is the power that we're interested in simulating. So we know what should be in the power meter, and this is a faithful copy of that in the simulator. So if I actually kind of run this up now, analysis, transient, because we're interested in stuff over time, and I run this, then I've got a few traces on the left hand side. So this green trace is what is appearing at that test point. Now that looks like it should do now, and there's going to be some further shaping happening in the actual real circuit. So if we take sort of the midpoint of this slope, 826 millivolts, and this one here 929, this is all negative millivolts because it's all on the negative side. That's about 100 millivolts difference, which is exactly what we're expecting. So what else have we got showing? We've got a few voltages showing on this top trace. The reason we've got it split into two is just to keep sensible scaling. So this blue signal here is the chopped input. So on here, it's just here labeled chop out. So we've got the voltage coming in, it goes into a 196k 15 ohm 196 ohm divider, which is roughly divided by 1000, so 145 millivolts turns into 155.388 microvolts at the source of this SVT, goes through here to chop out, and we've got the alternative chopping, which is the same as the actual meter, switching on these two in alternate switching on and off. So that should chop between 155 microvolts and 0 volts essentially. Now on the scale, so it fits, we've multiplied by 1000 and we've got 156.6 microvolts. So yeah, absolutely spot on. Everything's working fine. Fault finding wise then, I started off looking at the resistance here to make sure that I got the right resistor on, and the 15 ohm and the 196 ohm as well. This one's a little bit tricky because it's connected to a voltage divider on the other side. But essentially, yeah, if you disconnect the power and turn it all the way across, you get 196k. So that's fine, and these were fine too. But when I tested the voltage at this point here, which should be 155 microvolts, it was 68 microvolts. So it's kind of like, well, hang on a minute. If I've got the right voltage in and my divider is correct, how can I possibly have too low a voltage at that point? So if we look further back in the circuit, we can see that this switches on and off, and when this one's on and conducting through, it's just connected to that capacitor. So that shouldn't really be a problem. And when it's switched off, of course, that should be at full voltage with nothing connected at all. And of course this will be switched on, and that'll be at 0 volts. And then I realized, of course, that if both of these transistors are switched on at the same time, then this 15 ohm and 196 ohm are actually in parallel with the 15 ohm over here, the R2. So the next thing was to connect my scope to these. So I would expect, of course, to see a nice chop happening alternatively on both of these points. And first of all, checked it on the board connection. That's fine. I'd got alternative chops between 0 and minus 10 volts happening on each of these 2 points. So that's absolutely fine. So those are connectors on the edge of the board. Same on the resistor, same on the other side of the resistor, same on the gate on here, and no signal on J2 at all. So J2 wasn't switching, it was permanently connected and on. A quick delve into the board, and I found that there's a fault on the board, that actually that resistor isn't connected to that transistor at all. So I added in a bodge wire, and hey presto, that did the trick. Now to demonstrate what happens, I can actually do this in the simulator live. So I'm literally just going to break the connection between that resistor and the transistor. Ooh. And instantly the chop output looks horrible. So instead of having 150 microvolts, it's now got, let me have a look, 48 and 0, so it's got about 49 microvolts difference. So that's not very good. And if we move down to the actual meter, go for the sort of center point again, that's minus 866 and minus 893. Yeah, so so we've got 30 millivolts in the meter instead of 100 millivolts. So yeah, but the signal actually looks right. It's a nice stepped signal, and it's the right shape in the meter. It's just the wrong level. Soldering the bodge wire onto the gate of the transistor is really tiny, and I'm just bending it using a pair of tweezers so it doesn't snap off the transistor. So bending it using the tweezers, lining it across onto the resistor where it should be, and now I'll just solder that up. It's got to kind of tin everything because I don't want this to take very long, because if it takes too long it'll pop off the transistor. Okay, with that, power connected, so reference connected rather, power is connected here. That. Okay. Turn it on. Turn all on. Turn them off. All on. Oh yeah, this is looking much better. Okay, that's correct. Because I need to switch. I should be able to zero it. Zero dBm. Okay, just reattaching the. Just go for a second. I'm going to turn it on to internal. And we're still zero. That should be -5. I'm pretty happy with that. -10. -15. -20, -25 is where we're starting to lose linearity a bit. There it goes. And the other way, 20 dBm is the top. Perfect. 15, 10, 5. It's a success! So I've replaced the internal transformer, changed it to 15.8 volts. And reprinted the front panel actually just to make it a bit tidier, and we can see that the calibrator is set to 10 dB and is outputting 10.018, so better than the 0.2% error that we would expect, and the whole range is within the expected 0.2%, so I'm really happy with that. That's worked out well. Hope you enjoyed that. If you did, thumbs up. And if you could subscribe, that would be really helpful as well. I'll look at putting some of the circuit diagrams, etc., onto GitHub or something a little bit later. See you soon. Take care.